All right, folks, let's take a look at this example here again. So we're talking about two professors at a local college developed a new teaching curriculum designed to increase the students' grades in math classes. So in a typical, developmental math course, they're saying 57% of the students will complete the course with an A, B, or C grade. In this new experimental course, out of 18 students, 14 of them are, successfully completing the course with an A, B, or C grade. So they want to know, is the experimental course effective at the 0.025 level of significance for our alpha value? So, of course, since we're talking about in the typical course, 57% of the students completing their course. So based on that, we can come up with our null hypotheses. So the probability should be equal to that percentage of 0.57%. And then, when they're saying, is the experimental course effective? Of course, we want our alternative hypotheses to show that, we have a higher success rate than 57%. So of course, we are looking at, P being greater than 0.57 for the alternative hypotheses. So the first part they're asking us is to verify why the normal model may not be used to estimate the p-value over here. So they're asking us to find n times p naught times 1 minus p naught and try and see what that number comes out to be. So just to show you, where I got that answer from, we'll go to our Google Sheets over here. So you can see we have our p-value, x, n, and the level of significance. All of that I've kind of listed over here. When I take my 14 out of 18 for the experimental course, you can see that probability comes out to be 0.777 repeating. Now, to see why we cannot use normal model over here, you can see when we multiply n times p naught, so that's 18 times 0.57 times 1 minus 0.57, that value is coming out to be 4.4118, which is less than 10. And since it's less than 10, we cannot use the normal model to make this approximation. So that's our verification here. 4.4 less than 10, so we cannot use or may not use the normal model. So that means this is going to be a binomial experiment, and we're going to use the binomial probability distribution to estimate that p-value. So remember, for the binomial experiment, you have to have a fixed number of trials. You have to have two mutually exclusive outcomes, because your success and failure cannot happen at the same time. So they have to happen, separately, no overlap. Your trials, of course, have to be independent, and your probability of success has to be the same for each trial. And in our case, that fixed value is going to be 0.57 for each trial. And as you can see, I've also included that right over here in our Google Sheets with that same probability of 0.57 over here. So since this is a binomial probability distribution that we will have to use to determine the p-value, you actually want to use either the formula, you can use the binomial distribution table, or I can show you how to use StatCrunch to come up with this p-value also, which might be the easiest method out of all three of them. So go under Get More Help, and you will see you have the option for StatCrunch. So go ahead and click on that. And then once you get in here, I'm going to move this to the side a little bit so you can still kind of see how I came up with this. So go under Stat, then go under Calculators, and here you will see we have the binomial calculator. So click on that. Now, for us to be able to use this binomial calculator, I've again put some instructions over here. So you can see I'm saying use StatCrunch, and I'm giving you the n value because, of course, in that first part, you've got 18 students in this course. 14 of them have completed the course, successfully. And also remember, you have a alternative hypothesis of p being greater than 0.57. So this is a right tailed test. And since this is a right tail test, in our binomial experiment, you are going to use probability of X being greater than or equal to 14 because of this being a right-tailed test. So just kind of keep that in mind as you're working through this. And that's what I have over here. So let's get that calculator up again. Okay, so you will change your N value to 18, probability to 0.57. You know, of course, we'll need to change this number to 14 and then change your symbol to greater than, equal to. And when you click compute, you will see our number comes out to be the same as we had over here. So 0.058-21323. Our instructions are telling us to round this to 3 decimal places. And so you can see it came out to be 0.058. You know, obviously, as you can see, I had initially miscalculated this and I put in that p hat value of X divided by N, the 0.777 that I had over here, but you know, that was obviously the incorrect answer. So the right one should be the 0.058. So now you know how to calculate that. Once you have that, you will compare your p-value with your level of significance, which is the 0.025. And of course, 0.05 is greater than 0.025. So in this case, since my p-value came out to be greater than my level of significance, we cannot reject the null hypotheses. And basically, you do not have enough evidence, or there's insufficient evidence to tell us that the experimental course you know, is doing a better job or is more effective. So in this case, you will see we are saying do not reject the null hypotheses because the p-value is greater than alpha. You have insufficient evidence. Now, as you move forward, you will see they are changing our sample size, and now you have 54 students and 42 of them are completing the course with an A, B, or C grade. So you will see on the right-hand side, I've basically redone the calculations here with the new values. Level of significance is still going to stay the same. And you know what, give me a second here. Just gonna copy this over so you know that's the level of significance. Probability will still stay the same. Now we have 42 students out of 54 who are successfully completing the score with an course with an A, B, and C grade. You will notice that when I divided 14 by 18, that probability came out to be 0.777. When I divided 42 by 54, I am still getting that same probability of 0.777. The only difference is now we have a much larger population over here. And you know, that makes a difference when you have different, sorry, not population, sample sizes. So our probability is the same, but our sample size is different. Now, when you calculate the N times P naught times 1 minus P naught, you will see this is a larger value now. You have 13.23, which is a number larger than 10. So you can actually use the normal model here. On the previous one where you had a small sample size, you can see our number only came out to be 4.4, which was less than 10. So we were not able to use the normal model. But here, since you got 13 point something greater than 10, you can use the normal model. And so you can see 13.2, which is greater than 10. You can again make the assumption that the sample size is less than 5% of the population size, because as you can imagine, we have more than 54 students, you know, who are taking a math class. So we definitely have a much larger population size. So yeah, 54 will be less than 5% of that population. They're not explicitly telling us that this sample is randomly selected, but again, we can reasonably make that assumption. So we can assume that the sample is random. And like I said, since our check value here came out to be 13.2, which is greater than 10, you are able to use, so you may use the normal approximation. So first thing to use normal approximation would be to calculate the test statistics, the Z sub 0 value. So let's take a look at that. And you can see again, here's the formula from our textbook for the Z sub 0 value. And And to calculate this, you're taking your p hat, which is the 0.77777, repeating, minus the p naught, which is the 0.57 value here, dividing it by the square root of p naught times 1 minus p naught, and then divided by the n value of 54. So I've got that whole formula, as you can see, typed in here. And that gives us the 3.08, which is what they want us to round this to. Once you have found this test statistic or Z naught value, then we need to calculate our P value. And for this, you will see I'm telling you to use the normal, standard normal distribution table. So go in your table and find where your Z-score of 3.08 is going to be. So here's our table, and I'm of course on the positive side. So we go down to 3.0 on the left-hand side. So you can see 3.0 over here. And then of course we will need to use the 0.08 on the top over here. So that's going to be this column. But to try and get this all on the same screen, we're going to have to move this around a little bit. So here is our 3.0. This will be the 0.08 column. So you can see our probability is going to be 0.9990. Now remember, by default, your standard normal table is always giving you the area below the Z-score. So, we are at 3.08, and this area of 0.9990 is on the left-hand side. Again, let me remind you, we are looking at a right-tailed test, which means we are interested in calculating this area. So remember, for the bell curve, your entire area or percentage probability value is 100% or 1. So to calculate this right-tailed, we would have to do 1 minus the area on the left-hand side, which is going to be the 0.99999. So when you do 1 minus this number, and if it helps, you can write it as 1.0000 minus 0.9990. And as you can see, this will come out to be 0.0010 technically, but we're rounding it to 3 decimal places. So that's how you are calculating your p-value from here. So again, find the 3.08 in your table using the z-scores, and that will give you the percentage of 0.9990, and then subtract that from the value of 1 so that you can find that right-tailed area. So I'm going to clear this out, go back over here so you can see I have marked in our table what that probability came out to be for a z-score of less than 3.08 in that area. And then I am subtracting that from 1 to give me a p-value of 0.001. So when I compare that p-value of 0.001 to our level of significance, which is the 0.025, now you will see that my p-value is less than my level of significance. So my p-value is less than alpha. And in this case, we can reject the null hypotheses and say that we have sufficient evidence to conclude that our experiment course is going to be effective than the typical developmental course. So you can see we've got our test statistics, z sub 0, our p-value over here, and then based on that, we are saying, yes, reject the null hypotheses because the p-value is less than the level of significance, our alpha, and we have sufficient evidence. Now, the last part here is talking about explain the role that the sample size plays in the ability to reject statements in the null hypotheses. And, of course, when you have a small sample size, the evidence against the null, the statement in the null hypotheses must be substantial. And, of course, we did not have a substantial evidence because our sample size was so small. So, they're telling us one should be wary of the studies that do not reject the null hypotheses when the test was conducted with a small sample size. So you can see just the difference with the sample size makes a difference in if you can use the normal model or if you have to use the binomial experiment for that, and then what kind of results you can get from a small sample size to a relatively, larger sample size. So I hope, this kind of helps you to walk through the example and kind of see how we can come up with these values for this problem. All right, guys, I hope this helps. Take care.